Hi, my name is Pritesh, and this is the first in a series of lectures on flight performance, flight stability, all the way from pre-flight checks, taxi and takeoff, through to the en route phase, and then finally approach and landing. So, as an overview, some of the terms that you might come across are, flight mechanics, which deals with the motion of aircraft or spacecraft. So in that terms, it would be orbital mechanics. While it's under the influence of forces such as gravity, thrust, and atmospheric drag. Flight dynamics, on the other hand, is a slightly wider, more encompassing term. So it also covers performance stability, but then it also includes control of aircraft and spacecraft. Flight test is more focused on the development and gathering of data during flight. So that data that's captured can be used for a multitude of purposes, validation, and the development of models for things such as flight simulation. Are two key points there. So throughout these lectures, it'll be presented from the perspective of as an aerospace engineer, but there's quite a bit of overlap. So the concepts of, say, flight stability, flight performance are important to both aerospace engineers and pilots. The only difference there is that the perspective, an aerospace engineer is more focused on the design, the validation side. The pilot is focused purely on the operational side. So sort of a middle ground is, flight test engineers, flight test pilots, who need to be aware of, I guess, both those areas in detail. A simplified sort of concept, if you want to look at, designing an aircraft. Aircraft design is fairly, it's an iterative process. So once you've done the design, the validation takes place. Now this could be validating it purely, in terms of, say, numerical modeling. So you might be using CFD. Could be experimental. So you're looking at then validating, the designs that you've made through, wind tunnel testing. But ultimately, finally, it should be, tested on as an aircraft. So, essentially a flight test. So once an aircraft is certified for flight, meets all the airworthiness requirements, is able to get, say, a type certificate, operational licenses, then the operations take place. But it doesn't all quite end there, because any upgrades that take place, you have to go through the entire process all over again. So just things to keep in mind in terms of flight and what it sort of encompasses. Now the different phases of flight that an aircraft can have. So for a commercial aircraft, or a general aviation aircraft, normally you'll start off from pre-flight. So this makes sure that the aircraft is ready, and it's deemed safe to fly, because it's operating within its defined parameters. So taxiing to the runway, taking off, climbing whilst you're in the terminal area, then starting your en route phase, and finally, once you've reached your destination, approach, landing, and taxi. Now, a lot of the concepts, so as you can see, then an aircraft needs to be designed to be able to operate safely within all those phases of flight, so whether it's on the ground or in the air. And a lot of those concepts, such as flight stability, apply whether you're on the ground or in the air. Now, a couple of terms that we'll go through in this lecture today, so center of gravity, static stability, neutral stability, and weight and balance. I'm just going to go through, kind of define each of those terms, just to give you an idea of how it all fits together. Now, the center of gravity of an aircraft. Imagine you've got an aircraft, right? Longitudinal stability, you can take it as you have the aircraft, and if you're able to balance it just on one finger, I'm sort of cheating here, but you can see that if you were to move it further forward, aircraft would tip back. If you move the center of gravity too far back, it would actually tip forward. So all it is just finding that point where the aircraft is balanced essentially, and that's quite important because the stability of an aircraft is really based around that point, and exactly where it shifts to. So let's take phase one of the flight. You're looking at an aircraft which is sitting on the ramp or on the runway. What if you shifted the center of gravity too far back? Something like this might happen, and we haven't flown yet. So really, this is dependent on the type of landing gear configuration that you have, exactly where the mass of the aircraft is. So these sorts of things need to be taken into account. When you're looking at the other phases of flight, so in the rest of the phases of flight, you've actually taken off, you're in the air. The concept of the position of the center of gravity still remains the same. The only difference is now you don't have a landing gear acting as your main lever, but the aircraft, the forces acting on it now are dependent on the main wing, the tail, the fuselage, could be the engines, whole host of different forces acting on it. And the way these forces interact about the center of gravity leads to moments, and those moments influence the stability of that aircraft. So the textbook term for stability is essentially the tendency for an aircraft to return back, if there is a disturbance, essentially returning back to a state of equilibrium. Now you can split that into either static or dynamic, and disturbance could really be anything, such as a pilot could be putting in an input, could be a gust of wind, and it's all about how that aircraft reacts in that situation. Now, focusing just on static stability is essentially the initial tendency of the aircraft. So, just looking at your moment, static stability would be where the initial tendency is for the aircraft to return back. So, if you're looking at it in terms of longitudinal, it would essentially be the tendency for it to return back to straight and level flight. When we refer to neutral stability is really just a point, an imaginary point. If the center of gravity moves to that imaginary point and there is a disturbance, the aircraft will just sit there. It doesn't have enough of a restoring moment to return it back. And finally, if the center of gravity shifts any further back than that, then we refer to this as being statically unstable, which means that the aircraft will just continue to just rotate, and there's not enough of a restoring force to bring it back. Dynamic stability, on the other hand, is looking at the time response. So you have an initial response back, but you're looking at now that stability of the aircraft over a period of time. Static stability doesn't always imply dynamic stability, but static instability does imply dynamic instability. And what that really means is that if you do have an initial disturbance, the aircraft could return back, but that oscillation could get bigger and bigger and bigger. So it could be similar to divergent oscillation. Whereas at the same time, if you have divergence, the aircraft will not return back. So one of the key things that both a pilot and an aerospace engineer should be aware of is the concept of weight and balance. Now, if you're going to fly an aircraft, and in order to be allowed to fly it, the aircraft needs to be within operating parameters. These parameters are some of the things that are outlined in your pilot's operating handbook. A pilot's operating handbook is essentially a book which is specific to each aircraft, because different aircraft may have different configurations, different equipment on board, so they'll have different weight and balance requirements. So, things that are outlined in a POH, performance, weight, emergency procedures. Throughout this lecture series, I'll be using either a Cessna 172, which is a general aviation aircraft, or a Cosmic Eurostars, some of the examples that we'll go through. And the thing is, as a pilot, you'll be used to using a POH all the time, but you have to have a think, who ends up generating the values in the POH. So I'll sort of leave that to you guys to have a think about. So from the Cessna 172 POH, you have what they call a weight and balance graph. So a couple of things you have to keep in mind is that box defines the operating parameters of this particular aircraft. Now, if it says that the maximum takeoff weight is 2,550 pounds, it means that by exceeding this value, the aircraft isn't designed to operate safely, outside of this. So if you were to load the aircraft to say 2,700 pounds, if you did come in for a landing, you tend to find that, over a period of time, the landing gear, for example, is designed to take, enough of a force for an aircraft of 2,550. By exceeding that, you're stressing it outside of its initial design. So what you could do is you could essentially shorten the lifespan of that and make it unsafe to fly. Other things that might happen, you might not be able to climb at the climb rate that you initially intended, so you'd have a lower climb rate, and you may end up stressing other parts of the aircraft which it wasn't designed to do. So you've got a maximum sort of takeoff weight that you need to calculate for the aircraft. Now you'll probably see something like this in general aviation aircraft. You've got either a utility or a normal category. Utility is if the aircraft is, for this particular one, in order to be able to do certain maneuvers such as spins, if the center of gravity for this aircraft and its weight are within that particular box, then you're allowed to perform that. Otherwise, you can do all the maneuvers that you can do in that normal category aircraft can do. Now the two bands that you see, so on the you've got 147, which is the distance in front of the datum, rearward of the datum, and then you've also got the forward limit, which is 35 inches behind that datum point. So for aircraft, what you tend to find is the datum is usually taken as the firewall, which is where the engine gets fitted, because it's a point on the aircraft which doesn't change. Whereas you'll tend to find with a lot of flight mechanics books, the datum is taken from the leading edge of the main wing. Now we'll do some conversions in the future lectures in order to work between the two, because at the end of the day the concepts still remain the same. So the most important thing is here to work out the center of gravity of the aircraft, see if it fits within those bounds, and also to see if the weight of the aircraft is within those bounds. So before you fly, this is an exercise that needs to be completed, but at the same time it's important to know how these values come out to be. So again, how are these bounds generated? And this is something that we'll go throughout this lecture series and future ones. So where is this datum? So if you were to take the Cessna 172, you'll find that the reference datum sits right at that firewall point, and the distance between that to the center of gravity is just outlined there in that picture as x. So going through a weight and balance example, now earlier I said that one of the ways in order to work out the center of gravity of an aircraft is to find the point where it balances. It's not so easy to do with larger aircraft. So the process that you go through is you take a known weight of an aircraft. Usually it's referred to as the basic empty weight, which is given to you in a POH. Then you add the weight of the passengers, baggage, fuel. So if you're doing this in metric terms, you do it as mass, so you do it as kilograms, not pounds. But if you go through the process, you'll still get the same results. Now, that's the process you go through to get the final weight. Fairly easy, fairly straightforward. With getting the moments, you take the center of gravity off the aircraft at that basic MT weight, multiply that weight by that moment arm, the distance from the datum. So as long as you use the same reference datum for all of it, then you're okay. And then if you go through and divide the total moment by the total weight, you can find the center of gravity of the aircraft. So just to go through as an example, for a Cessna 172, if it had an empty weight of 1,672 pounds, that arm was 37 sort of inches behind the datum, you get a total moment of 63,368.8. Take the pilot weight, so I just put in a value of 180 pounds. Let's just say the pilot is flying on their own. They've got quite a bit of baggage, at about 80 pounds in the rear. And as you can see, the where the baggage is located is quite a bit further back than where the pilot's sitting, because the moment arm is 95 inches instead of 37. In order to do usable fuel, so the maximum fuel that a Cessna can carry is 53 gallons. A gallon of fuel weighs 6 pounds. So if you do the calculation, you have 318 pounds. The maximum weight comes out as 2,550, and then the total, and then you can put that value there. Go through for each of the weights, calculate the moment. So as you can see, the moment for the baggage is actually more than the moment for the pilot, because even though the pilot weighs more, the moment arm is quite a bit shorter. Same thing for the fuel. You'll get a total value of 92,574.8. Take that moment value, divide it by the total weight, and you'll have a center of gravity value. So once you have that center of gravity value, so remember those terms we went through earlier, so static instability, statically stable. So for this Cessna, more or less, this is just an approximation, but you can find that final bound, at 47.25 inches behind the datum. If the center of gravity moves any further back than that, then you can consider the aircraft to be statically unstable. So to make sure that the center of gravity is in a location where the aircraft can fly within within its design parameters, you can see that from the weight and balance example that this aircraft is, it would be cleared to be able to fly. But think of this as an iterative design change. If you were to make some changes to this aircraft, say if you changed the size of the wings or the aerofoil type, if you change the tailplane, how would that actually affect the static stability and of the characteristics of this aircraft? So you can see that it would actually change that that line in the back, the final. So it essentially changed the box. And throughout this lecture series, we'll go through and we'll step by step calculate how this is done. So the next lecture in the series is, again, now you've been cleared to fly from the ramp. You can taxi to the runway. Once you're at the runway, we'll do takeoff. But the important things with takeoff is you have to be able to determine what your climb performance will be. And this is for different reasons. It could be it changes due to atmospheric conditions, but at the same time, what if you upgraded the engine on an aircraft? Again, that would change your climb performance. So it's good to be able to go through an entire process to have confidence in the design changes that you make. So the reference textbook that's used throughout the lecture series is Nelson. So that's Flight Stability and Automatic Control. Other excellent references that you can definitely use: Anderson, Carpenter, and Cook.